So one aspect of these projects, which I didn't mention before, is that we do try to encourage students to get involved with social issues and diversity and energy conservation, a lot of things. And so you see that theme behind some of these, and you saw it clearly with hunters, and I think you'll see it with the next presentation too. So I'm going to turn it over to Caleb, and he's going to talk about his machine.
For my project, I did a Neuro-Prosthetic, and I'm just going to go over the overview of what it is and how it works. So the goal of my project was to develop a functioning prototype of a prosthetic hand that is controlled by the user's nerves and muscles. I also wanted to make sure that when it's fully completed, that the prosthetic device would be affordable for anyone who would need it, because most prosthetics out there are very expensive, and some people also can't afford them. So a basic prosthetic can mimic simple motor control of lost limbs, such as opening and closing a hand, but a more complex prosthetic will be able to control individual fingers to provide a more lifelike movements, and you'll be able to use the prosthetic as you would a normal hand. A Neuro-Prosthetic is a device that is controlled by the electrical impulses in your nervous system and muscles. These impulses are collected by electrodes that are either placed on the surface of your skin or implanted directly onto the nerves, and the signal is then sent to a microcontroller and an amplifier that will then control the prosthetic device. And why would you use the nervous system? The device would be much smaller because it is either flush with your skin, it only take up a little bit of area for the computer, and it would be even smaller if the electrodes were implanted in your arm. And there's no need for cables and levers like you would need in a mechanical prosthetic. And this has the ability to go beyond just prosthetics and being able to bypass broken nerves and restoring basic motor control of paralyzed limbs. And I chose the ulnar nerve because I made a prosthetic hand, and since the nerve is already in your arm, it controls the muscles in your forearm and hand, it just made sense to use that. And it's also the largest nerve in your arm. And it runs down from your shoulder, past your elbow, and into these three fingers. And the ulnar nerve is also when you hit your elbow, your whole arm tingles. And so, like when you hit your funny bone, and your whole arm tingles because you pinched the nerve. The ethical impact for having a Neuro-Prosthetic, and so the physical impact, you would need possible surgery if you chose to have the electrodes implanted directly on your nerves. There would be a learning curve when using the new device because you'd be using different muscles or using the same muscles differently than you would have before. But the benefits, you'd be regaining basic motor control with a lost or paralyzed limb, and patients will be able to return to their daily activities if the injury prevented them from doing so. And the biggest benefit, I think, is designing it and choosing pieces to make it that'll make it affordable and just as effective as the more expensive ones. So my system diagram shows the biggest pieces that would be needed to make this functional. So the first part is the electrodes that are on your skin, and the electrodes pick up the electrical signals in your muscles, and they bring that signal to an amplifier circuit. It takes the very small voltage and boosts it up to a usable voltage that the microcontroller can understand. And then the microcontroller is programmed to receive that input and output the proper signal to turn a servo motor. And the servo motor is used to open and close the prosthetic hand. So the first amplifier chip I used was the ED623, and it is manufactured by Analog Devices, and they make them usually as amplifier, and it's made by Texas Instruments, and these amplifiers are also low powered, and that also makes it better for battery power. And having a slew rate, which is the reaction time of the changing input to your output, and it's very high for this amplifier, and that's important because when you close your hand, the muscle signal is very short, so you need the amplifier to be able to react to that. And this has a reaction time of 3.6 volts per microsecond, so it's very fast. And with this chip, there are 2 amplifiers in each one, so that makes it much more compact. So this is my full amplifier circuit schematic, and with the chosen amplifiers connected, I assigned a gain to each part of the amplifier circuit, and the gain of each chip is determined by the ratio of the resistors. You can't really tell from the projector, but this up here is a 270,000 ohm resistor. This one's a 1,000. So each side of this amplifier has a gain of 270, and combined is 72,900. And then this one, it goes into this amplifier, which has a gain of 100. And the complete output of this specific circuit is the voltage going into the amplifier comes out 7 million times higher than going in. And I needed that much of an amplification because the voltage from your muscles is so tiny, and just running that with the microcontroller wouldn't pick it up. So I'm getting about 2.5 volts out, which is perfect for the microcontroller. So this was the completed circuit on the proto board, and you can see the similarities in it, but it's just a little bit of a mess. So this is the output signal of my amplifier, and the big jumps are when I close my hand, and that charges the capacitor, and the slope down is the capacitor just discharging. And by changing the ratio or changing the values of the capacitors and the resistors at the output, you can change how long the signal lasts and how fast it falls. And you need it, the slower it falls, the easier it is, or it doesn't discharge as much as fast. So you, by closing your hand and keeping it closed, it'll stay pretty constant at the peaks. So I chose the KL25Z Freedom Board microcontroller because it's low cost, and that was my goal, is to keep the cost as low as possible. And this board, I chose the board for its affordability and compatibility with add-ons and peripherals from other systems like Arduinos. And it has a vast amount of features, from touch capabilities, so you could adjust the sensitivity of the prosthetic if needed, as well as a gyroscope and an accelerometer. And I only used 4 pins on the microcontroller, which is the VCC, 5 volts, and the ground to supply power to the amplifier. And I used an input and an output. The input pin took the signal from my amplifier, and the output pin controlled the servo motor. And we used the C programming language to program the Freedom Board. And the software I wrote was to control the servo motor, and the servo motor would turn depending on the output the Freedom Board was given. And this is also a low power board, so running off the battery will be easy. So this was the code I had to write, and I tried to keep it as simple as possible, but being able to control individual fingers, you would need a separate loop right here for each servo motor you have. So this section right here is initializing all the pins I would need to use. So I have an input pin and an output pin. So when it goes in here, this loop, it loops forever. So it's checking to see if there's an input on port E1. And if there is, it'll turn the servo motor one direction. 2 milliseconds would turn the motor all the way to the right. That should be right. And the arm of the motor can turn its full width within at a speed of 60 degrees per 0.1 second. And it can do the whole 180-degree sweep in 0.3 seconds. And this diagram just shows the length, the size of the pulse width and the 20 millisecond pulse period. So this was the prosthetic hand I designed and made. And the final proof of concept design was made out of plexiglass tape and the plexiglass frame, and tape was used to form a hinge between the pieces, so it's very easy to move them. And the fishing line was run through straws and attached to each finger, and they were all tied together at the bottom. So when the servo motor turned, it would pull all the strings tight and close the fingers into a fist. And this is my system diagram for all the pieces there in the life. So I have the electrodes picking the electrical signal off my arms and bringing it to the amplifier circuit, and that goes to the microcontroller, which is battery powered, and onto the servo, which closes the prosthetic hand. So to complete this project, I would need a printed circuit board, and I needed a professional looking board that functioned just as well as my prototype board. And I built my amplifier circuit in an Eagle CAD printed circuit board design software. And what it does is it takes your schematic file that you design inside the program and creates a board layout that you can modify, and it gives you the board file right here, which then you can cut out and use just as a normal circuit board. And I designed the circuit board to fit directly on top of my microcontroller for a more compact design. And what I have left to do to complete my project is my project is 90% done at the time, but I have to finish my printed circuit board right here, and also design a fixture that'll hold the microcontroller, the amplifier circuit, and electrodes all on my arm. So it's just one small design that just fits on your arm. And I wanted to, as I stated before, I wanted to make it as affordable as possible. So as the cost of my material is exceeding the hand, because the hand will be the most expensive part. And since I haven't fully designed that yet, I didn't include it. So the microcontroller board is $14, and that's the most expensive part. But all the other components were relatively inexpensive, and you get all of them together with the indirect costs would change a little bit, but it's under $50 for the hardware to build the amplifier circuit and the microcontroller and everything. Any questions?
So you could use that for an industry person to pick up something that's very hot. You can have your hand pick it up. Your advantage is to pick up a very hot thing.
Yeah, you could have the applications for this are almost limitless because you can use it in construction fields, medical field, and probably even a military field. So you could just have a person out of harm's way controlling the thing that's doing whatever you need it to do.
You just put the sensors on the